Okay, now let's talk a bit more about the cracking. We'll do a recap on the cracking process. On the theory, now first of all, we said that the cracking is important because we crack heavier or the heavy hydrocarbons into smaller ones to meet the demand for the lighter hydrocarbons. Because the lighter hydrocarbons are more useful than the heavier ones, so the demand for this will be greater. So that's the purpose of cracking. Now, cracking has to be carried out through the catalyst. So we call it as the catalytic cracking. Now, what the catalyst means? Let's see whether you have to memorize it. Can you remember? Aluminum oxide, is it? Yeah. Okay, so aluminum oxide. Or we also use the silicon for oxide. Okay, so either this catalyst can be used for cracking. Now, usually the temperature for cracking has to be above 600 degrees Celsius. I know this is not in the syllabus, but just for your general information. It can actually run it at various temperature, but the minimum requirement is that it must be 600 and above. Okay, then the other thing is, when we crack the heavier hydrocarbons, it will definitely produce one of the products as an alkene. Now, this is one of the exam questions. So they say that, is it true, or which of the statement is true? One of the products of cracking must always be alkene. This is always true. Right now, regardless of what kind of heavy hydrocarbons it is, when it undergoes cracking, it will always produce one of the products as an alkene. So how do you tell? Look at the equation and see whether it tallies to the general formula of the alkene. So in this case, the dodecane broken down into the octane. This is an octane, but it also gives the butane. So this is the alkene. Okay. All right, so let's go into the question. The type of reactions of this is cracking. Cracking, and the two conditions required, can say that it must have a catalyst, and the other conditions will be the temperature must be higher than 600 degrees Celsius. Or we can just say that it requires high temperature to operate this cracking process. Okay, now what about part 3? How do we find the percentage mu, given that 1 mole of the dodecane will give only 22.8 grams of the octane? So a quick recap on the percentage here. So the 22.8 grams of the octane is what we have obtained, all right, from the reaction. But the theoretical amount of the octane may be more than 22.8. So let's find out what is the theoretical amount of the octane. Okay, so given that we have 1 mole of the dodecane, do you also agree that the number of moles of the octane is equivalent to 1 as well? Right, because based on the equation, all of them have the same mole ratio of 1. So this has 1 mole, this octane must also have 1 mole. Right? Okay, so once we found the number of moles of the octane, can we now find the mass of octane? That's the theoretical mass. Right, so we're going to take the number of moles multiplied by the MR of the octane, which is 8 times 12 plus 18 Okay, exactly what's the value for this? The mass of the octane. Sorry? Okay, 114 grams. Alright, so this is the theoretical mass of octane. Can you see it's much, much more than the actual amount of octane that was obtained? So what is the percentage mu? Will therefore be 22.8 divided by 114, and you multiply by 100%, and that should work out to 20%. Any questions? Can the two isomers of the butene, this one you should be very familiar. Alright, the first one is to draw the double bond on the first two carbon atoms. Okay, and the second isomer is whereby you change the position of the CC double bond to the second and the third carbon. So these are the two isomers. Alright, I need you to fill in the blanks for the hydrogens. Right, you can also get this answer from your notes. Okay, but remember, when you change the position of the CC double bond in the molecule, it will always considered to be isomer. Alright, now if you want to know about the name of this kind of isomer, right, it's actually called positional isomers. Just some extra information. Now, positional isomers are referring to isomers that have the same functional group, but their functional groups are attached to different carbon atoms. Alright, so we say that they are positional isomers because the position of the functional group are different in different isomers. Get it? Okay. So these are the two types of isomers of the butane. But at this level, no need to learn about positional isomers. It's just that some extra info for you. Right? Okay, then for part 2, one use of these isomers other than the fuels. Now, most of these isomers or the alkenes, right, are used to make plastics. Okay, alkenes are always used to make plastics. So if you ask for the common uses for alkenes, just write used to make plastics. Standard answer. All right. Then for part C, how would you distinguish between the two compounds where octane is a saturated hydrocarbon, okay, and the C4H8, this is known as a butene. Butene is an unsaturated hydrocarbon. I think there's a typo here. So it should be a butene, not a butane. All right, please make the change. It's butene. So we're going to use the aqueous bromine. So which will cause the aqueous bromine to decolorize? Elegantly. Which one? Is it the butene or the octane that causes the aqueous bromine to decolorize? It's always the butene, right? Yeah, the one is the CC double bond. The one the butene, which is in the family of the alkene, can cause the aqueous bromine to decolorize, even when there's no UV light. Right, so here we said that C4H8 decolorizes aqueous bromine under room temperature and pressure, but C8H18 does not decolorize aqueous bromine at all. Okay, so the alkane, which is in this case the octane, can only decolorize aqueous bromine if there's presence of the UV light. right? But in order for us to differentiate which one is alkene and which is alkane, we don't introduce the UV light. We can help if we can actually use the color change to help us to indicate which is which. All right, so that's the answer for